Good morning and welcome. I hope everybody is ready to blast off for our Engineering Tomorrow Space Day. Today is an amazing day. We have amazing speakers, amazing presenters, but really the star of the show is you and your students. We want to see what you guys create. We want while teachers, while you're in the classroom, take some pictures, take some videos, share them with us via email so that we can share them at the end of the day. And today, you guys are in for a treat. We have our amazing curriculum coordinator, Mr. Milton Davis, who's going to be leading you for the entire day. He's going to be here for the whole day. He's going to be here for the intro. He's going to be here for the breakout rooms. We're so excited to have him. I'm going to stop speaking and let Milton take it away.
Oh, thank you so much, Monica. And like you just said, we're going to blast off. I am so excited. It's Space Day. It is Space Day. Let me share my screen. Can you all see my screen? Give me a thumbs up. Thumbs up if you can see it. Thumbs up if you can see it. Nice. Excellent. 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 Before we jump into Space Day, I want to learn a little bit about you all. I wanted to be an astronaut. I always thought, like, what would I eat in space? If I had to eat in space for an entire week, what's the one thing that I would eat in space? So I need you all to jump into this Slido poll. You can type slido.com and then type those numbers 2102221. It's going to give us an opportunity to engage you a little bit. What is your favorite food? Just one. If you're going to take one food item to space, what would it be? What would it be? And like Monica said, we are blasting off today. Space Day. We're going to create some rockets. We're going to do it big. Look at they're eating healthy. They're eating healthy. I see Chick-fil-A. Chick-fil-A is in the chat. Some pizza. Chick-fil-A is coming in strong. A little pasta, some pineapples. Good old mom's cooking. They're taking their mom right into space. Taco Tuesday. Come on. McDonald's McCrispy. All right, I see you. A little sushi, some meatballs. Okay. Betsy, what's your favorite out there? What's your favorite, Constance? Monica? Type it in the
I
chat.
like pizza.
Oh, a little pizza. That's good. Some hot dogs. I see you, Zaire. Very nice. Oh, I'm definitely into some Chinese food. Someone said space yogurt. You all are ready to go. Excellent engagement. We may talk a little bit about that. Brad Peck said peanut butter. I think Brad knows I'm a huge peanut butter and jelly fan. That's my favorite. I could eat peanut butter and jelly sandwiches all day, breakfast, lunch, and dinner. All right, but what we're doing here today, and why we're so excited about today, is because it's all about space. We're gonna talk about space missions. We're gonna develop a launch vehicle, a rocket that enables space missions, and we will answer all of your space questions. You all sent in some outstanding questions. Hey, but I didn't develop this lab all by myself, right? I want to give a shout out to my buddy Travis, who helped develop the beginning of this lab. Betsy out there, she helped update it. But man, these absolutely outstanding. I think they were college mentors then. I think they're engineers now. Lauren and Katie, they killed this lab. You're probably wondering, who is this guy that's talking to you and how did I get into the STEM field? Well, it started with RC cars. I know you're like, an RC car, what is that? Well, we didn't have TikTok. We didn't have Snapchat, Monica. We didn't have Instagram, any of that stuff. So play basketball, play football, play chess, and I raced these RC cars for sure. The other thing I was really, really into was just all things space, TOEs, and I didn't have foot problems. I'm talking about theories of everything. And we'll talk about that today. How did this universe come into existence? I didn't enjoy reading, but I could read about space all day long. So I was going through high school, started questioning about space, but I didn't go to the best high school with the best technology. So I self-enrolled in a community college, and my counselor said, "Hey, Milton, you got to figure this thing out." So we mixed my love of RC cars. Well, that's kind of like engineering, and we mixed my love of the universe and space, and we landed and we launched with aerospace engineering. And I've been an aerospace engineer since 2001. And in the process, Mr. Belton, I love that image. I end up transferring to Purdue University. I am a boiler maker, boiler up from Indiana. Anyone out there from Indiana, give me a shout out. And then this is me as an intern, a very long time ago, interned at NASA since 2001. And we'll talk about internships as well. That is a great path into the space field. That's a great path into engineering. You get paid to play. You can't beat that, right? But what do I do? What do I do? So what I do is I lead a mission that is going to address what happens to spacecraft or satellites when they die. We're going to fix that. So type this in the chat. What do you think happens to a satellite when it dies, when it goes bad, when it loses power? What do you think happens when a satellite loses power? What do you think, Zaire? What do you think? Who else is out there? Daylight, Twilight from New Jersey. What do you think? Norfolk Technical Center. What do you think happens to a satellite when it goes bad? What do you think? Come on, give me a little bit. Give me some engagement. Communication, that's right. Loses the signal, it burns. Very nice. This is good. Come on, challenge prep. This is great stuff. You all are hitting the nail on the head. The communication may be lost. That's right. That's right. Excellent. And that part right there, oh, floats into orbit. That is so true, right? It could just continue to move away from the Earth. That's excellent. Yeah, and then we get all this, this space junk. So what you want to happen is you want it to come down, and as the friction from the air is moving against it, it'll burn up or ablate, and hopefully it'll end up in the ocean. But sometimes it ends up on large continents, and we don't want that, right? So one thing OSAN 1 is doing is we're trying to address that issue, and we're addressing it by in-space servicing. We upgrade satellites that have gone bad. But we also fix satellites that are not working. And then all that space junk that's created by all these satellites and all these collisions, we're going to find a way to clean that up. And that's all through in-space technology. And I want to give a shout out to St. Peter's Boys High School from New York. They asked, how do you do this? How do you enable this? And that's what I'm showing you in this video right here. What you're seeing here is that you enable this by catching the right speed, by catching the right orbit, and by catching the right trajectory. So what you're seeing is this satellite has got into the right orbit, and it's caught the satellite it wants to grab onto at the right speed, and it's gotten itself into the exact right orientation. So then it can grab onto that target satellite, open it up, and push it back into its correct orbit. That is how you do this. That is what they call this whole process, where it's called rendezvous and docking. Now what you're seeing is this. You're seeing in this image that we are cutting open the satellite so that we can refuel it. I mean, some satellites go bad, they run out of fuel. We're going to cut this satellite open, we're going to refuel it and place it back into its correct orbit. Great question, St. Peter's. All right. So what are you going to engineer today? What are you going to engineer today? We're going to talk about that. First, we're going to talk a little bit about the history. You're going to get a chance to travel through space flight history. You'll learn how we travel from the Earth to the moon to the stars, and you'll get a chance to build your own launch vehicle so that we can enable different missions that are in space. All kinds of different missions to answer all kinds of different questions. So with those questions, I have a question for you. What questions do you have about space? What questions do you have about space? What questions? Type those in the meeting chat, or you can place it right here in Slido. Going back to Slido, what questions do you have? This is good. This is good. We'll roll. What questions? Is it infinite? That's right. Expanding, infinite. What are the boundaries of space? That is an excellent question. Is it possible to explore all of it? The billions of light years of this expanse. That's a great. Do I believe in aliens? Yes, I do. Yes, I do. Man, this huge universe, you don't think there's some aliens? Come on, man. How does it smell? That's a great question. That's a great dark energy. Oh, we're gonna have to talk about dark energy. That is really, really good. Dark matter, dark energy. Does space really exist? We get those questions a lot, right, Betsy? Does it really exist? Let me look at the chat. How good is it in space? Yeah, this is excellent. Excellent, excellent, excellent. All right. I've had similar questions as well. What comes to my mind when I thought about space are we alone in the universe? You all had a similar question. I mean, this huge universe, are we alone? Right? And if we're not alone, how can we travel to such far distant regions so that we can investigate if we're truly alone or not? And to do that, I mean, you may have to travel through time, right? Or maybe you got to travel the speed of light in order to see other galaxies, right? Other galaxies that may host or may have the ability to host light based on the proximity of these planets to their sun, based on whether they have water, whether they can support life, right? Or are there planets that we can, other planets we can truly inhabit, right? And maybe, is there another planet out there, right, that is habitable? Let's say we fill up this planet too much, right, Brad? Maybe we got too many people here. We may want to check for another planet. All right. So those are some questions I've had as well. We'll talk about them today. But what are we going? One thing we need to answer though is the difference between aerospace engineering and astronautical engineering. We got a couple different labs. One is all about space being all the things that happen beyond our atmosphere. That's the astronautical part. And then the other part is the aeronautical part, which is everything that's happening on the ground, right? Up to about, let's just say, 1,000 to 2,000 kilometers. And if I were going to show you an example, the James Webb Space Telescope, which is a telescope that is truly investigating the origins and the spans of our universe. You all are asking how big it is. That's what James Webb's telescope is investigating. And on the ground, when we launch it, that's more about the aeronautical side, right? But after we launch it, and it's out there in space, and the telescope is unveiling and unassembling, right? And deploying and looking out to distant galaxies. Now we're in the astronautical part. And we're going to talk about both, but our focus today is truly astronautical, okay? So before I move on, you always have to know where you're starting to know where you're going. So we're going to talk a little bit about the past and the present and the future, okay? So it all started with Sputnik. You probably never heard of Sputnik, but it was the first human-made object that went into space, 23 inches about in diameter. This was the start of the space age, and it was the start of the space race. As soon as the Soviets got something in space, everybody else wanted to get involved. After Yuri Gagarin, the first man was in space, the United States developed their own capsule, the MA6 space capsule. And then after one human was in space, they wanted to send a lot of humans in space. So we started launching not just small objects, but people into space. And we realized we needed much better rockets. So this Saturn V weighs 6.2 million pounds and was able to take 24 people all the way to the moon. But 24 people wasn't enough. We moved on to the space shuttle, right? And the space shuttle completed 27 missions. And it wasn't just taking people to the moon. They were truly performing science in space laboratories. So even though we were able to reuse the shuttle itself, we couldn't reuse the rocket, right? So there's another school out there in Texas, Los Fresnos. Hopefully I pronounced that correctly. And they said, well, what role does industry, what role do contractors play in all of this? And what you all have developed for us is something like a reusable rocket. Never seen anything like this before. I mean, what you've done SpaceX has been able to do is take a rocket, launch something into space, and bring that same rocket back home and reuse it, which has been an absolute game changer. And the government almost exclusively uses rockets from industry like SpaceX. And even though that's so remarkable, the biggest thing we question is, what are you all going to do? What the innovation that you all will see 10 and 20 and 30 years down the line is truly, it's unbelievable. So with that in mind, if you were a scientist, if you were the owner of SpaceX, I don't know, if you were the owner of NASA and you wanted to investigate something, what would you want to investigate? What do you want to investigate in space? Let's see what we got in the chat. Someone said, can we talk about the possibility of establishing settlements on Venus? Sheesh. Excellent question. You know, Venus, that's a gaseous planet. That's going to be really tough, but maybe we can do it. You're right, 25 degrees Celsius. Great. Other planets. Thank you, Norfolk Technical Center. Great question. Other planets is another great one. Stars. Yeah. Distant stars. Excellent. Black holes. The rings of Saturn. Colonies. The colonies is a big one. I would love to see a colony on Moon or on Mars. I just think that would be just crazy, crazy cool. Excellent, 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 excellent. Nice. We think about the same thing at NASA. We think about interplanetary navigations, how to create these different mission designs. We think about Earth science, right? You know, how do we protect this Earth and keep it sustainable? Planetary science. I mean, space is not just a vacuum. There's magnetic activity, there's solar winds, there's solar disturbances. You know, what's the effect of all of that on our Earth? You know, astrophysics is what I'm really into because I want to know everything about the origins of the universe. How did God make this wonderful, beautiful planet that we are all inhabiting right now? So, with that, let's talk about what we send into space. We send payloads, and payloads are not just astronauts, right? That's a payload. A payload, any object that goes in space. A payload also could be a satellite. It could be the Mars rover, which is doing some really dope science on Moon, on Mars. It could be the James Webb Space Telescope, right? And when we design these, right, different payloads, we think about the cost, we think about its capability and size, and we think about the conditions that has to survive as well. All of that goes into play. And then spacecraft, what we're going to focus on today, and sending a spacecraft into space type of science. And this is just showing you some examples. All right. But here's a question.
What?
How do you get payloads into space? How do you get a payload into space? How do you get a payload into space? How do you do it? What do we use? Type that in the chat. What do we use to get payloads in there? There you go. Yeah. Shamari, Gail, I hope I got that right. Challenge Prep, Jonathan. Yeah. Yeah. It's rockets. It's rockets. I got a great video I want to show you all about the launch of rockets.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Tower clear.
We've got a roll program.
Plus 30 seconds.
Wow. Wow. Amazing. I mean, in that time, they didn't have SpaceX. They didn't have Saturn V. They didn't have all these, you know, crazy rockets. And for them to experience seeing a rocket launch and then the first humans going into space to complete missions, it was an absolute game changer for them. Crazy, wonderful.
T-minus 15 seconds. Guidance is internal.
I'll skip this next one.
Computers,
But
primary control
we'll skip
of all.
You know, when a rocket goes into space, it experiences just a crazy, crazy environment. You got to imagine it's trying to overcome gravity when you're just launching straight, right? Not a plane that's kind of like it's coming off the pad and it's going horizontally. I'm talking straight vertical with millions of pounds of weight is one of the most difficult things that you can do. But in addition to that, the air, the acoustic energy, the different layers of the atmosphere it has to travel through, the changes in temperature. It's really, really warm on the ground, but outside of our mesosphere and our stratosphere, it gets really, really cold and hot. This rocket has to survive all of that in order to achieve placing the payload in the space. And that's going to be your challenge as well that you're going to develop. So what's a rocket? A rocket is used to take the payload to space. And what you're seeing over time is the more we want to place in the space, the larger larger the rocket has had to become. So you can see the satellites have truly grown over time. And inside of them, what's amazing is 90% of the volume, 90% of the mass is the rocket. It's not the payload that we want to take into space. It's not what we want to use to investigate, right? It's the rocket. So what we need to do is we need to come up with better ways to optimize the design of our rockets. And that's why this rocket or this lab is all about you all designing innovative rocket propulsion systems. Now, a propulsion system is what helps generate thrust, right? And we have two systems we use. One of them is kind of like a bottle rocket, solid rocket engine, very, very powerful. As soon as you let it rip, there's no control. It just goes, right? Pretty much no control. But then you have the liquid rocket engine, not as much power, but you have the ability with the fuel, the oxidizer, the pump to throttle and control it, to turn it off, to speed it up, right? So I got a good question from one of the schools, Mercy Academy and Barbara Goldman, about how does Newton's third law play into this? Well, Newton's third law says for every action, there's an equal and opposite reaction. And we know that as the conservation of momentum. So inside of this rocket, as the pressure builds up, that's the action. It only has one direction to go. The reaction is outside of the rocket. And this is why you don't need air to make this happen, because it's all about the balance of action and reaction and the conservation of that momentum. So now that we've gotten through all of that history, it finally is time. It is time for us to start building our rocket. Hey, why don't we take our materials out? Let's do that. Let's take these materials out real quick. Let's see what we got in our bag. See what we have in our bag. So here is my space material bag. I'm taking out some materials. Hey, maybe this will be good for the body. I have my pump here to place the air inside of my balloon. And look at that. You got a bunch of different balloons that you can use. What do you think these rubber bands are for? What do you think the rubber bands are for, right? Got a bunch of different balloons, some small, some large. We got some rubber bands here for sure. Maybe those are to help secure our straw directly to our rocket there. We got our straw there. And here's something that's really important that you got to see. Yeah, Dalen Perez, I see those materials. Here's something that's really important right here. Look at that. This is what you're going to use to clamp your rocket balloon closed so the air doesn't come out, right? In the pictures you want to see on the next page, you'll see some clamps. But here I want you to show these are some special clamps that my good buddy Jose, he hooked us up and he gave us some special clamps just for you, okay? And then this is the fishing line that you're going to use. So the straw is going to go onto the balloon, right? And then the fishing line inside of here is going to go into the straw, and that is how you're going to have liftoff. That's how you're going to have liftoff, okay? Let's look at those materials one more time. Let's see what you got. See, you got some paper clips. The goal is to carry as many paper clips up to the top of the oh, I heard that. Okay. Then you have your fishing line, which that's your reel. That's how you're going to go up to the top. And again, we have some clips to your air pump. All right. Okay. And this is your goal. You're going to construct a balloon powered rocket that carries the most weight. The weight is the paper clips carries the most weight all the way to the top of the ceiling. We're going all the way up. And as you're thinking about this different design, this design that you're developing, what challenges do you predict you'll have when designing and launching this balloon rocket? What are some challenges you think you'll have, Duval? What are some challenges you think you have? Yeah, what are some challenges? Think about that. What do you think is going to be a little difficult with this to make this rocket balloon system that's going to go all the way up to the ceiling? What are some challenges?
Challenge Prep Academy just sent me a message. They say getting it to fly, and it might be a bit too large, or the balloon may pop. These are some of the challenges they're saying that might happen.
Excellent. Excellent. Thank you, Monica. Monica could just present this for me. I don't even know I'm here. Someone also said balance. Yeah, balance. I mean, if the weight is lopsided and it's not going up straight, that's going to create a lot of friction that's not going to allow us to move all the way to the top. Excellent. That's Kay Patterson Huck. Excellent. Good questions. Good comments. Good question. And the way that we address this, all this inquiry, all these questions, and we use the engineering design process. We got a tool for you. You don't have to do it all alone. There's a great process. I use the same process when I've developed many different satellites, many different instruments. I start just by doing a little research online, rocket designs, balloons, overcoming friction, balance, mass, all of those different things you all brought up. That's the learn part of this. And after I've learned, I've done some research, then I'll start my design. And when you design, this has been a game changer for me, is I literally will design on paper first before I build it. Because if I come up with a pretty good design on paper, I have a better chance of a decent build. Something I'm not going to have to build over and over and over again. And after I build it, I test it. And if I test it and it doesn't work, that's okay. I just keep going through this entire process until I come up with something that's absolutely magnificent. All right. So do you have any questions about this project? What questions do you think you have about the project? Do you have any ideas that you're already coming up with? I'm seeing some stuff come in my personal chat. That's good. You can don't be nervous. You can place those out in the meeting chat. That's all right. All right. I see some questions. Great. So here's some ideas for you. One, you want to make sure you find a method to secure the payload. Now, you got to take all of these paper clips, as many as you can, up to the ceiling. You got to find a way to secure it. Maybe you'll use a cup. Maybe you'll use a bag. Maybe you'll tape the paper clips right onto the top of the balloon. And then some of you all talked about balance. Like, what if my rocket is turning or twisting? Well, you could use some fins. That's why we gave you the paper, the cardstock. The fins can help you orient that rocket to make sure it's not twisting and turning too much. And then some of you all say, I don't have enough power. Well, maybe you can use multiple balloons or multi-stage balloons, right? You got multi-stage balloons and you got multiple balloons to give you more power to go all the way up to the top. But first, use at least one straw. We need at least one straw. Make a good launch system. That's the string or the fishing line that goes from the top to bottom. Make sure that's really secure. And hey, that main structure, it's got to be reusable. That's why we gave the cardstock. We want to save on materials. And then you want it to be able to hold as much mass as possible. So somebody asks, hey, what are we using the ping pong for? Well, there's two reasons. One, you could use that as the payload that you launch to the top. Also, we have a really nice extension, which I'm going to show you at the end, that instead of making a vertical rocket, you make a horizontal rocket that drops the ping pong, which is almost like the Mars rover, right in the right spot on Mars. I don't know, at a cave, at a water site. I don't know exactly where it needs to be. It's another challenge. If you complete that challenge, Engineer Tomorrow is going to absolutely love it. I'm going to show you some of that because you asked. Great question. All right, here's some up. We gave you some ideas. Don't forget about the clamp that we gave you, the little clips we gave you to make sure you can secure it on the end. That's good stuff. And you're probably wondering, like, what is staging? Well, staging is when you let's say normally with rockets, we don't use just one rocket system. There's a huge, heavy rocket system to help us get off the ground. And one of you schools asked us, you asked me about this, like, hey, what do you do about all this mass that you're getting rid of? We generate more thrust. That's what we do. So that first stage we get rid of, right? Then there's a second stage that helps us get into orbit. And then there's a third stage that finally allows us to really operate in space, right? So we're multiple rockets are burned at different times in flight. And we're multi-staging to take advantage of the fact that we can get rid of some mass and go a little faster, get a little more delta V, a little more velocity, right? Okay. So I want to show you this video was done by Katie. You can see her in real time making her own kind of rocket balloon. Look at those paper clips. You got to think about where you're going to place those paper clips, okay? And then you can see here a sample. I'm trying to pause that. You can see a sample rocket launch.
10. Not 3, 2, 1.
Forward this just a little bit.
6.
All right, look
7,
at that rocket.
5. Bro, my brain. You want to count?
Okay.
4. You want to count?
They're having a little fun.
2.
Okay.
1.
Look at this.
Wow.
Cool. Hey, you're going to do much better. Faster rocket, more weight. What are the paper clips for? That's the weight. The paper clips represent the James Webb Space Telescope. That's the mass that you got to carry all the way up. All right? All the way up. Man, you all are asking
3.
good questions here. So, once you've completed this lab, we've got some extensions for you. And because you all showed up today, we are going to send you, or we may have already sent you, some special extension materials. So not only can you complete the vertical rocket balloon, but you can get down with this stomp rocket. Oh man, you want to see my buddy Betsy and her stomp rocket? Look at Betsy. Look at Betsy. Look at this.
Starting.
Let me do that one more time. Did you see that? Did you see Betsy in the
Starting.
stomp rocket? Yeah, look at her. She's gonna catch it. Bam. That could be you. You can make it in your house. You can make it outside, and this is how you do it. Good job, Betsy, Brianna, and Molly. And this is how you do it. Here are some of those materials. You got a pipe. You got some pipe connectors. You got a bottle. We gave you an L tube, some tape. And this is where all of your pressure is coming from this bottle. And once you stomp on it, all the air is released. And that pressure goes into this closed system of the rocket. And Newton's third law again, action and reaction, it launches. It just launches. Now, maybe you won't complete this today. I hope you complete it today. That would be kind of nice. But maybe you won't complete this today. But if you complete this, please send after today or today, send us some pictures, send us some videos. We would love to show off your rocket engineering skills. Okay. So with that, I want to say thank you all so much. This has been a really, really great session for our intro, and I'm going to hand it off to Monica to talk to you about the next steps.
Before we go to next steps, everybody, let's give Milton a big round of applause for their introduction to space. I hope you guys are all excited to start building those amazing rockets, and it is time. It is